Hello, everyone. Paul here to talk about topographic maps. And so, topographic maps are how we display the three-dimensional surface of the Earth in two dimensions. And we do that using contour lines. And so, I'm going to explain how contour lines work, and then we're going to look at some additional information that you can find on a topographic map. And then you got an exercise with some questions and things. But I think that after watching this video and reading what I've written, you all should be good to go with that. But of course, as always, if you have questions, you should feel free to ask them. So topographic maps, once again, use contour lines to display the elevations that we see on the Earth's surface. And so what a contour line is it is a line of equal elevation, right? And so we're looking here at the Mount Hood map. And if we look over in this section of it, we can see these lines running along here. You can see how this one is labeled 5,400. That means that it is 5,400 feet above sea level, right? This one here is 5,600. This one here is 5,800. So we can see that we're going uphill, in this direction, right? The closer together contour lines are, the steeper the slope is, right? So here, this is a fairly gentle slope, whereas over here, this is a fairly steep slope, right? So the closer together they are, the steeper the slope is. In between these thicker contour lines that we call index contours, you can see the thinner contour lines that kind of fill in the gaps here between these index contours. And so what we want to know, though, is, if we want to know the elevation, for example, there, well, that contour line's not labeled. So now what we need to do is we need to know the contour interval. And so if we look down here on the map, we look down here, we see right here contour interval 40 feet. That means that there's 40 feet in between each contour line. So if we go back up here to the area we were looking at, so if that's 5,200, then that line right there is 5,240. This line here is 5,280, etc., etc. The contour interval varies from one map to another. For example, if I look at a contour of a topographic map here of Florida, we see here, let me go ahead and make this a little bit bigger. And there we go. If we look here, we see here the contour interval is only 5 feet, right? It's a lot less elevation difference between Florida and the side of a volcano in the Cascade Range, right? So when you're dealing with a contour map, you want to make sure that you check out the contour interval, so you don't think something is a great huge mountain when it's really just maybe a little hill. Now, because contour lines represent areas of equal elevation rather. What a hill looks like on a contour map is a series of concentric circles, right? So you can see here we have a hill. It's kind of got two peaks on it. But, when you see these bullseye-looking things on a contour map, that's a hill. The problem, of course, is a hole would look the same way, right? If I had a depression, a closed-in depression on a contour map, it would also look like a series of concentric circles. So now we could look at the elevations and tell, we can see this is going up, but, it might not be big enough. You might not have an index contour handy. So how will we tell, a series of concentric circles that is a hill from a series of concentric circles that is a hole? Well, let's take a look. If I go back to the map of Florida, and I look right here, there's a sinkhole, right? And you can see the little tick marks, right? Those little tick marks. Let me make this even bigger, actually. Let's go ahead and make this 200%. There we go, right? And so you can see that, up here, for example, you've got a hill, right? You've got some concentric circles showing that there's a hill, right? Here's some other hills over here. right? Notice that we're only 150 feet above sea level because, we're in Florida, right? And so you kind of got a little bit of a flat top hill here, right? Not, the contour lines here are pretty far apart. They're closer together here, so this slope is a little bit steeper. This is kind of flat, but right here, and I'm going to go ahead and pop the magnification up one or two more times, we can see a hole, right? It's a series of concentric circles, but look at the little tick marks there. Those little tick marks tell you that no, the elevation here is going down, not up, right? And so sometimes that's obvious. Sometimes there's a lake in the bottom of it, like there is over here, or at least a marsh. Other times it might not be obvious what's going on, and so it's very, very handy to be able to tell that. A few somewhat random things here. Contour lines will never cross. Right? If two contour lines cross, that means that one point has two different elevations, right? That really kind of doesn't happen, okay? Now, there are times, and let me see if I can find this really quickly here. Let me zoom out a little bit. If you do have a cliff, contour lines will maybe come together, right? Because if you think about a cliff, that is, a very, very steep, very, very steep slope, right? And if we look here on the north end of the Mount Hood quadrangle, we can see these maps are called quadrangles, by the way. You can see here something that they've even labeled steel cliff, right? Where the contour lines kind of come together. And if the cliff is steep enough, i.e. pretty much vertical, then yeah, from above you will see something like this where contour lines come together, but they don't ever cross, right? You don't have that. Contour lines will always make a circle. Maybe not inside of your map, but they will always make a circle. They always kind of come back on each other. Maybe not in your map. Another thing about contour lines, let me show you. I just went the wrong way, sorry. Let me show you another thing, another handy thing about contour lines. And that is when they cross a stream, they always V in the upstream direction, right? And if I come back over here, let me zoom in a little bit more again. Actually, let me zoom in a whole bunch here. And so we can see here a relatively flat area, relatively speaking, for this part of the world. And here's a stream. And you can see what happens here as the contour lines, let me zoom out just a little bit. You can see what happens as the contour lines cross the stream. They make a V in the upstream direction. Now let's think a little bit about why that is, right? So if I'm walking along, and I am going to zoom this in a little bit more. If I'm walking along, and let's say I'm just walking along here at 5,400 feet, right? And I want to walk at 5,400 feet. Okay, so I'm walking along and I'm walking along. Everything up here is higher than 5,400. Everything here is lower, so I'm just walking along, and then I come to a stream. Well, that stream is cut down into the ground a bit, and so if I just step into the middle of that stream, I just stepped down. I don't want to step down. I want to stay at 5,400, right? So what I have to do is I have to kind of step in the uphill direction a bit, right, to keep at 5,400 when I'm in the stream. And then I have to step back downhill a bit to stay at 5,400 to compensate for the fact that this stream has cut its way down into the ground a bit, right? And so when you see streams on a contour map, and you see the contour lines crossing them, they always V upstream. Now here it's kind of obvious, 5,600, 5,000. This is the downhill direction to the southwest, right? But it's not always obvious. It's not always obvious, and so sometimes you might have to look and see what direction are the contour lines being in, right, to get an idea, to figure out what direction that stream is moving. So those are contour lines. And they're very, very handy. And I keep zooming in rather than out. They're very handy. Once you kind of learn with it, you can look at a map and kind of tell at a glance what's going on here, right? And we can see, that we've got a big steep. It takes a minute to load. These are very big files. But you can see here that we've got a big steep volcano here at the north end of the map, which makes sense. This is which one is this? I forget now. This is Mount Hood. That's right. So okay, now there's some more information on here along the bottom of the map. Let's take a look at that because this is also good stuff to know. Geologists use these maps all the time for all kinds of things. So okay, so over here, and they're all the same. And so over here, first of all, you just have some information about the dates when all these data were taken and things like that. So if you're really, really worried about things like that, you've got this information here. We're not going to worry too much about this. Over here, though, we have the declination diagram. This tells us, first of all, what direction north is. North is up. Okay, it just is. Doesn't have to be. I'm staring at a map on my wall right now where north is kind of up and to the left. Okay, but on these maps, north will always be up, which means north is up. That means west is to the left, east is to the right, and south is down. Okay, now, but we have three different lines here. The one with the little star is true north. That's actually north. That line points to where the axis of the Earth's rotation is, right? That's north. Okay. It also has grid north, which is the lines of longitude on the map. It's more or less true north. There's going to be a little bit of difference just because the Earth is round and there's projection issues, but let's not worry too much about that. Magnetic north, though, we do want to worry about. Okay, your compass doesn't point at the North Pole, right, where the axis of rotation is. Your compass points at the North Magnetic Pole, according to the Earth's magnetic field. Those two things are not the same. The magnetic field is not perfectly aligned with the North Pole, so your magnetic compass will not point at the North Pole. And so if you're going to navigate with that, you're going to need to know the difference between the North Pole and the magnetic North Pole, right? That's what this tells you. This tells you that it's, 14 degrees difference between 14 degrees 52, basically 15 degrees difference between true north and magnetic north. And a good compass will allow you to set that into it so that now when you're navigating with your compass, you're not off by, 15 degrees everywhere you go. The declination varies, right? If we come back to Florida and I look at the declination diagram, it's different. It's very different, actually. It's over here. And yeah, it's in a different direction. It's not nearly as much. So, when you go into a new area, first thing a geologist does is we pull out our compass and we set the magnetic declination on it, because otherwise you're not going to be able to navigate. This box down here has to do with the UTM system, which we're not going to worry about. Then we have a scale. We have a ratio scale, 1 to 24,000, right? So that means that 1 inch on the map equals 24,000 inches on the ground, or 1 centimeter on the map equals 24,000 centimeters, 1 mile, right? It's just a ratio. It doesn't matter what unit you use. Now, for our purposes, if you're going to use that ratio scale to measure something, make sure your magnification is set at 100. Right? That way, yeah, that really is. If I wanted to know, for example, I don't know, let's just find something to measure, right? If I just wanted to know the distance from here to here, and I was going to use the ratio scale, I need this to be at 100, right? So that when I measure this in inches, it really is, in inches. And so, I would measure that, I don't know, what is that, a couple of inches, right? And so maybe it's 2 inches. That means that it's 48,000 inches on the ground, right? Well, we don't measure things in inches. Divide it by 12 to turn it into feet, and then maybe divide it by 5,280 to turn it into miles if you really feel you need to. Or you can use one of these bar scales. Now, for the bar scales, we can up the we can jack the magnification back up, right? So I can put this at 200 now. Okay, and I can use a bar scale to measure something. Let's go to Mount St. Helens just for fun. And so here's Mount St. Helens. And let's say that we wanted to know, let me up the magnification a little bit. Maybe let's say we want to know how far it was, I don't know, across that crater there, right? We want to know how far it is from here to here. Well, if I put a piece of paper on my screen and I made a tick mark there and I made a tick mark there, then I could come down to my scales, right? And I could lay my piece of paper here, my tick mark is there, maybe my tick mark is, I don't know, there, or maybe it's probably about there. So it's about a mile across there. Once again, actually measure it. Don't just eyeball it the way I am, but you get the idea, right? If I want to know, a distance on the map, if I make a couple tick marks on a piece of paper, then I can lay those directly on this if I want to know feet, right? Maybe on this if I wanted to know it in miles, or maybe on this if I wanted to know it in kilometers, right? Ratio scales and bar scales are both very handy depending on kind of what you're doing, okay? If you're going to use the ratio scale, though, once again, set your magnification at 100 so that when you measure it, you actually are measuring it. But these scales allow you to measure distances on the map so that how far things are from each other. Let's go back to Mount Hood again. And so, yeah, we already know about the contour interval, 40 feet. Make sure you check it, right? Make sure you know what your contour interval is, because once again, it's very different here than it was on the one in Florida. Okay, over here, you have a map of the state that your quadrangle is in, showing you where it is, so you know roughly where you are. And then this is a really handy thing. This is a diagram that shows you the maps that are around this map. So if you run off of the map, you know what one you need to get, right? If I take this back out to 100 real quick, I can see that if I want to look at Mount Hood ends up being, just by sheer bad luck, load. There we go. Mount Hood actually ends up being kind of at the top of this map, right? I can only see, really part of the volcano on this map, right? Well, if I go back down here, it tells me that the next map to the north is number 2. That's Mount Hood North. Well, I happen to have that one right there. And so, yeah, right? So there's the rest of Mount Hood now on the south side of this map, right? Very handy thing. If you're working in the field and you realize, wait a second, I'm going to run off of this map, get the other map. Make sure you have it, right? You can order these as paper copies from the United States Geological Survey, or you can download them like I've done here. And I will put a link to the place you can do that on the exercise. And so let me go back here. And so, okay, so there's where we are in the state. Let me up the magnification again. So there's where we are in the state. There's the maps around this one, right? And so if you run off it to the east, you're going to need the Badger Lake quadrangle. If you run off it to the southeast, you're going to want the Post Point quadrangle, etc., etc. Then we have just a key to the roads and things like that, which is also handy. And then you have the name of the map and then the year that it was produced, also very handy. So there's a lot of good information along the bottom of this map. And then you have the contour lines that tell you the topography of the area, and that is, of course, the entire point. One more thing I want to mention, and that is these numbers here, which are the latitude and longitude of the corners of the map. So this line along the bottom here is a line of latitude. We use latitude to measure our distance north or south of the equator. And lines of latitude run east-west. And so if I run across this line of latitude, it runs into that number, 45.25 degrees north. If it was 45.25 south, it would be negative 45.25. And so if I look, for example, on the other side of the map, it's also 45.25, right? It's the same line of latitude running along the bottom of the map. We measure distance east or west of the equator using longitude. And so lines of longitude run north and south. And so this corner of the map here is 100. This side of the map, this western edge of the map, is 121.75 west, which we shorthand as negative 121.75 degrees west. Right. If I come over here, that number is going to change. 121.62. Right, it's different. Why? It's a different line of longitude. Right, this line of latitude down here is 45.25, but if I go to the north, the northern corner, it's not going to be 45.25 anymore. It's going to be 45.37. Right, not a huge difference, but it's a difference. Okay, so these bits right here tell us the latitude and longitude of the corner of the map. So once again, the top and the bottom of the map are going to be lines of latitude, and the east and west sides of the map, the sides of the map, are going to be lines of longitude. The way I remember which number goes with which side is I say if I run across here and run across here, it runs into the number I want, right? So if I want to know the latitude for the northern corner, northern edge rather, I come across and it runs into 43.75, right? If I want to know the longitude of this, I just follow it up and it runs into 121.75, right? So that's how I keep all that straight. Do not concern yourselves with these numbers. These have to do with the section and township and range system, which we are not going to go into. If you need to learn that, you can learn it. It's not difficult, but we're not going to worry too much about it. Alrighty, I believe that's everything you need to know about topographic maps to do the exercise. So now you're ready to read the exercise, do the exercise, download the maps that I've gotten for you. And like I said, I will link to the USGS website where you can get these for yourself. So that if you're going to go somewhere, you can grab the topographic map from there and have a look at the features. And then that would be really cool, because then you can look at the features and look at them on the map and kind of get an idea about what things on the ground look like versus what things on the map look like. But a little bit of practice, and eventually you'll be able to just glance at one of these and just visualize what everything looks like. Okay, y'all take care, and I'll talk with you later. Bye-bye.